Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy in my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on Current Initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Paul Douglas Tougaw. He's the Dean of the College of Engineering at Valparaiso University. I hope I said it right. We're going to talk about quantum dots and his research. So, Paul, a.k.a. Doug, thanks for coming.
Hey, it's great to be here today. Thanks for having me. You can just call me Doug.
Okay. Yeah, thank you. Well, tell me a bit about your background, and then I want to ask you about your current work.
Absolutely. Well, so my background is that I have a bachelor's degree in electrical engineering, and then my master's degree and PhD are both in electrical engineering, but really in applied physics. And so the problems that we tackled were applying physics, especially the physics of quantum mechanics, to solve problems that were relevant to electrical engineering. We call that Quantum-dot Cellular Automata, or QCA for short, because that's quite a mouthful. So QCA is really the work that I've been working on now for 31 years.
What is QCA, though, in like super basic terms, and then we can, contextualize it from there?
Absolutely. So I'm going to take a step back a little bit further and get a run up to what QCA actually is. Quantum effects are the behavior of objects that are at a very, very small scale. Essentially, when you get down to about 1 nanometer, so that's a thousandth of a millionth of a meter, a billionth of a meter. When you get down to that scale or smaller, a new type of physics takes effect, and that is quantum mechanics. And quantum mechanics has been a real drag on electrical circuit design for the last 20 years, as our circuits have gotten down to that range of nanometer scale. And so when we begin to encounter these quantum effects, they actually are undesirable. They're actually giving us behavior that is not what we expect or not what we want. What we want is for the atoms and the electrons to behave very normally according to the physics of things that are about the size of our bodies. But as we get down to the smaller and smaller and smaller scales, no longer do they behave in that way. No longer, for example, are they entirely a particle. They can be a particle, and at the same time, they can also exhibit the behavior of a wave. So this is actually limiting some of the improvements that we're seeing to computer hardware today. We're no longer are we able to continue to see that doubling of computer speed and density that we saw for so many decades. If you notice, when you go to look at computers today, they're all pretty much leveled out. Yes, they vary, of course, depending on the price that you're willing and able to pay. But by and large, we're leveling out in the speed and the clock speed of those computers. And the reason for that,
I've noticed that for like 10 years already. They don't seem to be advancing nearly as fast.
Exactly. And the main reason for that, or one of the main reasons for that, is because quantum effects are limiting our continued improvements. Now, another reason for that is that it gets extremely expensive to build these chips to be smaller and smaller and smaller and faster and faster. But quantum effects is one of the reasons why it is so expensive. Imagine, just as an analogy, think, if I wanted to continue to improve the speed of a car by a factor of 2 every 6 or 7 years, eventually wind resistance would become a real problem. If I'm driving that car 500 miles per hour, wind resistance is really going to become an issue. And in the same way, quantum mechanics or quantum behaviors are kind of the wind resistance of modern electronics. So what QCA does is it doesn't see the quantum effects as being resistance. It sees the quantum effects as the way to actually perform the calculations. So we're completely flipping it on its head. And rather than trying to overcome quantum effects, we're trying to use quantum effects to perform the same exact calculations.
Well, like in a transistor, from what I understand, if the gate on it gets thin enough, you'll have electron tunneling. But can you deliberately use electron tunneling reliably to turn on and off a transistor, for instance?
Everything you said is exactly correct right up until they turn on and off a transistor. I will say this. Here's the way that I think of conventional electronics, which are all transistor-based. You're all turning currents on and off. It's sort of like you have a flow of water, and that flow of water can be like the Mississippi River, or it could be down to just like a faucet in your sink. So you can be turning the faucet on and off, and that sort of represents the faucet on as a 1, faucet off as a 0. Or rather than having to constantly be pushing energy into that system, instead you could just fill a Dixie cup. And you'd be like, okay, if the Dixie cup has water in it, then that's going to be a 1. And if the Dixie cup is empty, that's going to be a 0. And so rather than thinking of the flow of charge, we just think of the presence or absence of charge as representing the 1 or the 0.
So how would you harness a quantum effect, let's say, in a transistor? What would that look like?
So yeah, we're kind of going opposite the paradigm of the transistor. I think, again, the transistor is about the flow of current, whereas what we're really trying to do is we lay out what are called quantum dots. So quantum dots are simply like, you can think of this as like a little deserted island. And just as if you've seen the cartoon of the deserted island where there's one palm tree, and there's really just room for one person to sit on that island. And that's kind of the way that we think of a quantum dot. There is room for one electron to sit on that island. We lay out a group of 4 of these quantum dots at the corners of a square, and then we populate that square with a total of 2 electrons. They're either going to lean toward the right or they're going to lean toward the left. And so we say that if they're leaning toward the right, that we call that a binary 1. If they're leaning toward the left, we call that a binary 0. But it's really about the configuration of the charges rather than the flow of the charges.
Are you talking about the spin of the electrons, or is it not intrinsic to the electrons? It's the arrangement of them and how they are.
That's a really insightful question, because there is an alternative way to do the work that we do called spintronics. And spintronics does, in fact, use the spin of the electron. A spin up would be a binary 1, and a spin down would be a binary 0. That's very, very similar to the work that we're doing. The work that I do is not based on electron spin, though. It is based on the location of the charges.
So what determines are they released from the 4 corners, the electrons? And, how does this work literally mechanistically?
Yeah, it's very much like what you said, that it's all about the electron tunneling. Electrons at a large scale, they can't really tunnel, and tunneling is a weird thing, right? So quantum mechanics is really so, in so many ways, violates our intuition. But electron tunneling is basically to say it can be in one place, and there's a thing in the middle that's completely forbidden, and it can never, ever be there. and it can be in another place on the other side of that barrier. It's kind of like it is absolutely impossible to climb this fence. This fence is infinitely tall, and yet when I look at one moment, the electron is on one side of the fence, and when I look a moment later, the electron's on the other side of the fence. In our world, that is absolutely impossible. It's a violation of everything we know about, the continuity of a person's existence or the persistence of an object. But in the quantum realm, it really can be possible to move from one location to the other without being in the middle at any time. And so that's what we're really doing here, is that we just have these 4 quantum dots, and the electrons have the ability to move among the 4 quantum dots. So they can move from the top right to the bottom right, or from the bottom left to the top left. They can move around inside of the cell without ever actually being in the middle, in the parts where they're forbidden from existing. And so we place other charges. We place other charges near this cell to make some of those dots more desirable or less desirable. And it's really hard to do this without a picture. But if you think of a square, and then if you think of, okay, well, I'm going to find a way to make, say, the top left corner undesirable. One of the ways that I could do that, for example, is to move another electron nearby. And if I move another electron nearby the top left corner, well, now the electrons are going to move out of the top left corner. And then really the only way that they can really spread themselves out as far as possible is then to move to the top right corner and the bottom left corner. And in that way, we've clicked it into the binary 1 configuration just by having an electrostatic interaction with another electron nearby.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
So are the possible positions in this square, are they energy wells, or what would be the attractant for an electron to go into one of those specific positions?
Boy, you ask great questions. So the 4 sites, the 4 quantum dots, those are in fact energy wells. And we think of them as being infinitely deep energy wells. They're not actually infinitely deep, but in practice, for our work, they really are. We're able to occupy that cell with exactly 2 electrons by bringing another electrode up very close to it and then putting the appropriate voltage on that electrode. So everything it's sort of like we're steering the motion, or we're steering the location of these electrons by moving other charges nearby. And the most important thing is that if I put 2 of these cells next to each other, and if for one reason one of them is tilting to the right, then that is going to force the adjacent cell to tilt to the right as well. And if I put one next to that, it's going to tilt to the right, tilt to the right, tilt to the right. And in that way, information can flow down a whole line of these cells. I can also make arrangements of these cells that can do useful calculations. And this is really why QCA matters, is because I can do an inverter or a NOT gate. I can also do an AND gate and an OR gate using nothing but QCA cells. And so if you have an inverter and an AND, or you have an inverter and an OR, you have a complete set of binary logic. And so we can actually perform any Boolean operation using these QCA cells. We can also store data inside of these cells, and that means that we have a complete set of computer architecture capabilities using QCA devices only.
Yeah, that's really cool. What are the dimensions, like the sweet spot dimensions of the cells, and what's the residence time and the calculation, on, off, left, right, lean time change?
Absolutely. So I'll say that the research that I started doing a long time ago was talking about these being, on the scale of a few tens of nanometers, because we just didn't want to be overly optimistic and hope that we could get down to, say, 1 nanometer. But I will also say that quantum mechanics gets stronger the smaller you get, and therefore these cells get stronger. They operate better the smaller they become, which is it's just completely turning that paradigm on its head, because we've been concerned about we can't get smaller. Well, now it's going to work better the smaller we can get. So I would say, if we're probably never going to get down below maybe 1 nanometer for a side of one of these squares, because that's really now we're talking about the scale of maybe 10 atoms. Even if we were to make these out of a molecular basis, it's going to be very challenging to get down below 1 nanometer. That is kind of an effective limit, unless we can figure out ways to do this in a different way other than a molecule. But so far, that's the best that we've been able to come up with. In terms of the switching times, I think we're going to see a factor of improvement of maybe another factor of 100 as compared to our current computer operations. So if we're looking at computers that are currently at 5 gigahertz, I would not be at all surprised to see a QCA device that would be operating at 500 gigahertz.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
That's amazing. What's that going to allow computers to do? Let's say it's for, I'm going to put some of these chips in my smartphone. What will that allow me to do? Or is it more industrial applications or larger ones?
Well, as with everything, the very first things are going to be the industrial applications, and those where we really need additional computational abilities. I think of, like the National Weather Service, being able to predict the formation of a hurricane, the path of a hurricane. If we had 100 times more computational power than we have today, we could make those predictions more confidently, and we could tell people, on Tuesday, you must be evacuated from this part of the country. I could imagine even today we have computer programs that can say read a mammogram, and it can read it. In some cases, it can read it more effectively than any human. Well, if we could get it even more effective, then we'd be able to predict. Oh, you don't have cancer yet, but in a year you're going to develop cancer, and that would be something that, boy, what an amazing improvement that would be. I think that honestly, probably the number one place for improving, where we can be able to put applications of this into effect, are in machine learning and artificial intelligence. That's a place where I think over the next decade, we're going to just see leaps and bounds. And I think that the new capabilities of AI and machine learning are really just going to be enhanced by the work we can do with quantum computing.
Yeah, with, again, like the chipset that's in my smartphone, if it increases 100-fold, I guess we can already get some low level, I guess, of AI on our devices, but I guess this would allow a very robust level of AI on even small devices, handheld, right?
I believe that's true. And I'll also say that it uses far, far less power than traditional transistor technologies. If you just think about, again, that the faucet is constantly using power, whereas the Dixie cup, once you fill it, it's not really drawing any more power. So I would say that at that point, then the cell phone battery life is going to only be limited by the brightness of your screen and by how much you're actually connecting to the Wi-Fi and to the cell phone network. The actual processor inside the phone is probably going to be pretty negligible in terms of its power use. That could say, rather than charging the battery once a day, which is what I have to do, or sometimes even twice a day, I might charge it only, say, once every 3 or 4 days, which would also be a substantial improvement.
Well, if the on-off power requirements become too low or too little, what's to prevent the device from accidentally turning on or off? Or, can they be protected or isolated so that doesn't happen?
Absolutely. So as with all quantum computing, we have to be very careful about errors. Because one thing that our traditional silicon, conventional electronic devices are very good at is not having errors. We don't tolerate even a single error in our computer. If I were doing a spreadsheet and I saw that a number was wrong, I wouldn't even know how to react to that, because computers just simply don't make mistakes. Now, part of the answer to that is we could have error detection and error correction algorithms. If you're at a factor of 100 improvement, you can pull 10% of that off and use it to detect whether there's been an error and to correct that error if necessary. Heck, you could even run 2 calculations in parallel, and let's imagine that you have an error rate of maybe 1 in 10,000. Well, if you get 2 parallel processes that give exactly the same result, you will have an extraordinarily high level of confidence that both of them got the correct result. If one of them is wrong, or if they disagree, then you'll know by definition that one of them is wrong, and you'll need to repeat that calculation.
Okay, so there's plenty of room for error correction and still increase speed. So let's say you can get 100-fold faster, even if you get 50-fold faster, but then the rest of it goes towards error correction, you still end up in a much better place.
Absolutely. And I would also say there are also a number of places where tiny little errors don't mean as much. Things like if you've got a large number of calculations that are all contributing to a result, maybe if one of those had an incorrect result, but it was one of 1,000, then that wouldn't really make a big difference.
Makes sense. Okay. How far along are you in the creation of these? Like, have you been able to create mini computers, or is there X number of cells you've been able to link together?
So my research has really focused on the simulation of these devices. And I'll tell you, I started doing this research at Notre Dame in 1991. And in 1991, they said, boy, in 25 or 30 years, we're going to be able to build these things. And that's a tough pill to swallow when you're a graduate student, to know that you're going to have to wait until you're an old man to be able to see these things working. But it's now 30 years later, and they're actually beginning to build these cells. There have been a number of researchers that have built, I would say in the ballpark of 10 cells, probably 5 to 10 cells, and we're able to see the logical operations that we predicted we would see. So now it's really just a matter of turning the crank and improving fabrication technology and improving the reliability of these fabrication methods, so we'll be able to actually build these devices that I've been dreaming of for so long.
Well, now that some people are able to build, 5 or 10 cells, now that reality is hitting, what kind of unexpected issues are they facing? Why can't they scale yet to 100 or 1,000 or 10 or a million, et cetera?
Yeah, so I don't want to step into another person's domain, because I don't know as much about the fabrication as I do about the scientific operation of the devices. I will tell you a couple of things that are unexpected, and one of them is that we have to operate these currently at very low temperatures. So we're looking at, you would have to have, a few tens of Kelvin, for example. Now, that's actually not as bad as it sounds, because you can actually generate that temperature with something that's about the size of a dorm refrigerator. We don't want to have a dorm refrigerator attached to each one of our computers. And so one of the things that we're going to find is that as we continue to shrink the size smaller and smaller and smaller, it will be able to operate at higher and higher temperatures. My advisor in grad school always said, we know that biology works at room temperature. And so these quantum interactions that are occurring in our bodies, they're actually operating at room temperature. And so we are very confident that as we shrink these devices down, we'll be able to find room temperature operation. That's just one example of a challenge that we're currently facing.
Okay. What do you think is going to be the next watershed in terms of temperature? You said tens of kelvins, which sounds a heck of a lot better than, millikelvin or nanokelvin.
Exactly.
But what would be like a huge step forward?
Well, I think the next step will probably be, I could imagine if we can get to close to room temperature, if we could get it down to just say 0 Celsius, that would be another big step forward, because that's something that we can generate without having to have any fancy sort of technology. Even though I was referring to the size of that freezer, it's still a pretty high-tech freezer. And so if we can get to 0 Celsius, now we're talking about something that isn't going to have to be any special technology. It can just be a regular freezer.
So in your modeling, what are some of the effects that I don't know. I mean, do you coordinate actively with the people that are actually building these systems in order to inform the modeling, or what's your interaction with them?
Absolutely. So it's essential that the people who are doing the theoretical calculations are kind of the pathfinders. They're kind of the trailblazers. They say, okay, I've now spent 5 years figuring out exactly how to lay out this structure. And so to the people who are designing the fabrication methods, here is exactly a structure that we would like to ask you to build. And so once they're able to build it, then we can verify that it gives the correct operation. So for example, at Notre Dame and at several other research institutions across the country, there are teams of people who are composed of the theoretical physicists and the construction, the fabrication physicists. Here at Valparaiso University, I've progressed into the dean's office, and so it's difficult for me to continue to be as active in the research as I once was, but I know that there are other researchers who are still very active in this field.
Yeah, so what are some of the necessary technologies that work with this quantum cellular automata technology that are vital to improve to get this viable for commercial applications?
Two of the biggest challenges are inputs and outputs. If you think about something that is so incredibly small that we're talking about just maybe a dozen atoms that would compose this device, how do you get the inputs from the outside world, where the inputs are, the size of our hand or the size of something that is not on a quantum scale? it's actually very challenging to get the inputs into the device. And there are researchers, I just recently read a paper from Baylor University where they're developing all kinds of new technologies for inputting devices, inputting signals into a QCA system. And then the outputs are maybe even more challenging because you have to sense the presence or absence of an electron without disturbing that electron. And there are some very good methods for doing that, but it is a real challenge. You know, I often feel like it's like trying to reach out and just pick a single BB off of the head of a pen without knocking the pen or the BB over. And it's that, but multiplied by a billion. So it is a very, very challenging task to get the inputs and the outputs to the system.
Well, why is the input signal strength just orders and orders of magnitude too much, and it has to be, I guess, attenuated to the point where it doesn't blow up the system?
So that's an important aspect of it. I would say another part of it is that if you think about this square, we need to make it so that it pushes it diagonally in one direction or the other. If we just bring the signal in, say, adjacent to the left side of the square, it's going to push both of the electrons to the right side of the square. We don't want that. We want it to be diagonal, either leaning to the right or leaning to the left. And so what we really need to do is bring that signal in adjacent to one of the four corners rather than to an entire side of the device. And that really is much, much more challenging.
What would be the ideal arrangement? You know, I'm picturing like if it's in a diamond shape arrangement, so one corner is close to the source, and again, they spread out like a diamond pattern. Would that make it work, or is it head-on? Like, it doesn't matter if they're arranged as just squares and the source sees the side of a square versus the corner of a square.
Yeah, that might be a good way to approach it. You could also think of having a wire that starts out big. You know, let's imagine a wire that starts out being 1 millimeter wide, which is really big for these things. But then, and you apply the voltage to that wire, but then over the length of the wire, it shrinks down as sort of like an arrowhead. And then it gets to just the very, very tip of it, just approaches one corner of the square. That might be another approach. There are a lot of different approaches to it. Right now, early on in this technology, one of the challenges is to figure out which one of those is the best way to do it. Conventional microelectronics face the same challenges. It's just a question of what is the best way to get those inputs in.
Are there other geometries you're contemplating, like maybe circular ones with wells spaced along the circle edge at certain intervals, or is it squares best?
You know, there really are some other options. We looked at devices that didn't just have four corners, but maybe would have 5 or 6 or 7 or 8 vertices. It was one of the real challenges that we faced was wire crossings. It's kind of like if you had all the roads in the world all had to be at exactly the same level, and they didn't have stop signs or stoplights. You couldn't have overpasses or underpasses, and yet you had to be able to pass data horizontally and vertically. One of the solutions that we thought about for trying to solve that problem was a cell that had 8 sides. There would sort of be like two different squares rotated by 45 degrees. That didn't work out, but we did find some good ways to get the signals to cross each other.
Well, what about looking at the grain structure or the crystalline structure of various compounds and mimicking that? Perhaps there's some that nature has solved this problem already for you.
Absolutely. Biomimicry is really important, not just biomimicry, but you look at something that is already working. And one of my favorite sayings is, if it has been done, it can be done. And so we always look for ways in which the sort of the world has already done something. We've investigated a lot of options, and the square really does seem to be the one that clicks the hardest into one of 2 bistable states. It's really important for the binary operations that it be either a hard click to the right or a hard click to the left. Any other configuration that we've tried either doesn't have 2 states, or the 2 states don't click quite as hard as they do in a square.
Okay, very interesting. Well, what from here, how long until it becomes, again, commercially viable, and what do you think the first instance of that will be? What will it look like?
Yeah, I want to be optimistic. I don't want to look at it through rose-colored glasses. I want to just say, I believe that within 10 years, we will have commercially viable QCA devices. I think that the first place that they'll be used is in the same sorts of applications where supercomputers are used today. I think that 10 years is reasonable, but is also, that's a good stretch goal for researchers to work toward.
Okay, well, very good. What's the best place for people to learn more about the device? I don't know if you have pictures, anything on a website or explainer videos, or where can people go to find out more?
So it's interesting. This is still very much a scholarly pursuit, and so it's there aren't a lot of YouTube videos out there. There are some really good Wikipedia pages, but you always got to check the sources on the Wikipedia pages. The place that I go is Google Scholar. So if I'm looking for to find out what is the new research in this area, I go to Google Scholars and I type in Quantum-dot Cellular Automata or just QCA.
Okay. Well, very good. Doug, thanks so much for coming on the podcast, and I appreciate your clear explanations of something that sounds to be very complicated, so thank you.
It's absolutely my pleasure. Thank you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.